Welcome to day 2. Just a reminder, this morning we'll have tutorials. You don't need to sit with your project team during the mornings. You can mix it up, and we actually encourage that, get a chance to meet new people and have new conversations. Does anyone have any questions or announcements relevant to the full group before we get started that they wanted to bring up? Great. Well, I think a few people will still be filtering in. We're going to start this morning. Today is kind of like the bread and butter of the core tools of using Python for geospatial analysis. So most of us work both with vector and raster data in different forms. So that's our focus throughout the day. And to start things off, I'll hand it over to Emilio, who's going to cover the raster piece.
Vector.
Boy, I'm not awake yet. Vector.
Yeah, same here.
Same.
I'm not the morning person. Hi, so you've heard from me, but we're recording this, so I guess I'll introduce myself again. I'm Emilio Mayorga. I'm a research scientist at the University of Washington Applied Physics Lab, which is that away at the other end of campus. It's a pretty diverse group. My background originally is in the sciences, in oceanography and biogeochemistry, but like many people in data sciences are probably here, I've had a path that took me into doing data science and data systems, and that's what I do most of the time now. Like Anthony said, I will be talking about vectors, or vector in the geographical information system sense. And, well, as he said more specifically, this is the beginning of something of a shift towards emphasizing, or tutorials that emphasize tools that you will actually use to launch into your project, to do stuff, process data, manage data, as opposed to the overall tools for how to manage your work with GitHub, etc. This is the Geohackweek schedule page. So if you go there, you can follow along. You can see for Tuesday, there's vector tools. I already clicked on that, but if you click on that, if you want to follow along on your computer, thank you. Well, there it is, but we'll also be showing that you were exposed to this software carpentry template yesterday. We'll be following that along, and then in about 15 minutes, we'll launch into Jupyter Notebooks and to enhance on stuff. So we'll be talking, I'll start out with some conceptual descriptions of what vector data is, how we describe it, what common formats are there, but not to give you a comprehensive description of formats, but rather to focus on the tools we'll be using today and this week. And then launch into actual Jupyter Notebooks with code that to teach you about the concepts, but I'll expose you to the concept, but also to serve as resources that you can go back to throughout the week as you work on your project and beyond. So first, a quick poll, I guess. How many of you have had decent exposure with geographical information systems? Just raise your hand. Oh my God, that's almost all of you. Okay. And maybe this was asked yesterday, but I can't remember. How many of you have some Python background? Okay, that's most of you too. And within that Python background, how many of you have used pandas? Thank you. Wow. You made all of our jobs easier. I'll still go over some things that you already know. I just wanted to highlight some terminology that it's not just to be a professor here. I'm not a professor. I'm a research scientist. But to emphasize certain terms and language that you will find repeatedly in the software that we'll be using. And it'll be very handy to be on that same core set of vocabulary, if you will. If for those of you who may not be as strong in GIS or Python, well, for those of you who are, if there are people in your group, in your table who are not as strong, please help each other to the extent that's possible. We'll have some free time or break times when you can ask questions both to your neighbors and to anyone. Pretty basic, but I'll remind you that a vector is a term commonly used in GIS to refer to discrete geometries, as opposed to raster that are continuous variations of any property like temperature on the surface or on air. So they refer to descriptions of features on land or water that have sharp boundaries. The Open Geospatial Consortium, it's a standards body or a geographical or geospatial data body, defined a while ago and standardized a set of geometric objects and the operations that can be performed on them that have been really widely adopted by both commercial and open source software. Not that the concepts didn't exist before, but it crystallized this concept and terminology, and I'll give you a very quick summary of the important concepts. This concept or this standard, it's called simple features, representing or focusing, like most of GIS, on two-dimensional planar geometries. It also defines other more complex objects like curves and surfaces, but we won't touch on that today. We will be focusing on the most basic and common types, the stuff that you operate on a daily basis in GIS, and that's made up of 3 types: points, lines, and polygons as single entities, so 1 point, 1 line, 1 polygon, and collections of those, of each of those. So what's called multi-point, multi-line, multi-polygon. And you see some examples of that in here. So you have the geometries defined by this entities or geometric types. And typically, each of those entities are associated with attributes. If we're dealing with a data set, a GIS data set of states, for example, the attributes could be the name. It could be some national code that ties into the census, or the area, population, and so on. So a feature refers to that for one object, one geometric object, it will, whenever you see the term feature, it will include both the geometry and the attributes associated with that. And very rarely are you operating with one feature, one polygon, one point. Typically, you're operating on multiples or collections of those. And that is referred to as a feature collection. So keep that in mind, that feature collection, feature includes geometry and attributes. Again, this is a 10-mile view of GIS in 5 minutes. Another core, or vector GIS, core element of vector geospatial world, I guess, is the ability to do operations on vectors. And that, here's just a brief list of what that is. Typically, they can be described as overlays. You take 2 layers. They could be polygons for states, dots for field sites, for example, and you overlay them. And you bring the attributes from one into the other, or you filter out depending on spatial matching. There are all sorts of operations. Some involve a single data set or a single feature collection, for example, a buffering, expanding the boundaries. Again, we won't go over the whole set of operations in any comprehensive way. We will illustrate some of this and illustrate how GeoPandas and other tools implement them so that you can use them. And finally, same goes for projections. So how the geometries and coordinates are represented on this planar surface. You probably all know and have heard that projections are really important when you're operating on your data. You have to know what projection you're working on to get accurate results. Again, I'm not going to go in detail on this. We will, most of the time, I think in this week, we'll be working in lat long. And that's often referred to as unprojected or geodetic. It's got all sorts of names. The one test that I'll give you tomorrow, it's the EPSG code, 4326. I'll see if I can remember the test. And there are really good reasons to be using lat long. They're very convenient, but they're also, when you measure, when you try to calculate areas or distances, it's not straightforward and they can be highly distorted. So very often, especially for applications that are continental or subcontinental to highly local, you'll be preferring to use a projection that is that gives you that is defined in linear coordinates like meters. And we'll have examples of working on both projections and both types and converting from one to another. Just a brief, this is not a comprehensive review of common GIS vector data formats, but I'll be emphasizing throughout this presentation standards, partly because they define a common mechanism for both commercial and open source software to interoperate. So they define a target that allows to communicate and pass data freely. In terms of data encoding, some of the common standards to pay attention to are especially well-known text, and it has its analog called well-known binary. There is GML that I won't get into, it's pretty complex, and GeoJSON. You'll be hearing GeoJSON more and more the more I speak and throughout the week. Well-known text, you probably won't be seeing it a lot, but it is fairly important. Many of you have probably been exposed to the spatial components of relational databases like PostGIS in PostgreSQL or the spatial component of SQL Server. Typically, the way the data are stored or accessed from these spatial databases is through well-known text or well-known binary. And we'll touch on that very briefly. But basically, there are string representations of these geometries. And you can see some of the examples. It's fairly intuitive. But for the most part, it's useful to know what they are and useful to know that they exist. But most of the time, you won't be using it. GeoJSON, it's becoming a lingua and GeoJSON-like objects. In other words, GeoJSON could be a file that you get that is an ASCII file or strings, and it's got a content. But it could be just an object in memory that is using a GeoJSON data structure. So it's built on JSON, and hopefully most of you have been exposed to the JSON format that is widely used in the web. It's almost the data packaging format in web applications because it's so straightforward to pass it on among applications, to map it into Python dictionaries, and so on. And GeoJSON just added a geospatial element to that, to describing vector information. It also maps, JSON and therefore GeoJSON maps really readily into other languages like JavaScript. Because GeoJSON has become so common, again, it's not that it's perfect for every single application, but certainly web application, it's a very, very useful and very common, and also for passing around between tools, between APIs, between software tools. To facilitate that passing around of data, this method or function or style has been defined called the geo interface. And we'll see examples of that as we launch into the notebooks. So basically, different Python libraries that do different things, if they adopt this geo interface function, they can pass data in a common form that looks like GeoJSON that other libraries can accept. And this, in the best of cases, can be transparent, but sometimes you have to call it explicitly. And again, we'll see some of this. I've put some tools for handling GeoJSON, or listed some of them. One thing to note that is very cool, and yet another reason to like GeoJSON, is that GitHub handles them intelligently. If you drop a GeoJSON file, as long as it's not huge, in a repository, when you go to it, you'll see a map. It's not a map that you'll publish a paper on, but it's fantastic for communicating the content. It's even clickable. So it's if you turn your vector data into GeoJSON and drop it on GitHub, it's a very nice and simple way to even share information and share visualizations with your colleagues. Just a brief listing of common formats that you have probably heard of. Shapefiles for GIS vector formats. They are still the most widely used format, for better or for worse. They're an awful format, but they do the job, and they are used by every single software. So typically, it's the least common denominator that you'll want to use, and they're definitely more efficient than GeoJSON because they're binary. I'll barely touch on them here, but they are supported by just about every software. And like I said, there are a lot of relational databases that have a spatial component, and we'll touch on some of those, and PostGIS also. Okay, and we are getting very close to fun. Okay, so from this point on, this episode and the next one is basically one notebook. Each of the episodes is one notebook. You can follow along. I guess you have three options, depending on what style you prefer for following along. We have this static version in this in the software carpentry template that you can just follow that along if you want. We also have, let's see, this is on, what's it called? Jupyter Hub. I'll be running it live on Jupyter Hub, so you can run it on your own also. Go to Tutorials, Content Vector, and Notebooks, and that's where you find them. We'll start with the intro, obviously. But also, if you want to have an intermediate, not quite this static, fully static and slightly converted version of the notebook, but something that looks, it is the notebook, just not running it live. I've included this link. Open the Jupyter Notebook in NB Viewer. Now click on it just to show you what it looks like. But also to, I don't remember if NB Viewer was mentioned last week or yesterday. And if it wasn't, it's worth being aware of it. It's this, you can see it's nbviewer.jupyter.org. Basically, if you have a Jupyter Notebook anywhere on the web, and especially in GitHub, but it's not it makes it really convenient in GitHub, but it could be anywhere on the web. This free application or website from the Jupyter team renders the notebook so that, and the beauty of this, and part of what's compelling about Jupyter Notebooks is that you can share a Jupyter Notebook or communicate a notebook to anyone that you work with, and they don't have to have anything installed. Now, you probably saw yesterday, I'm pretty sure you saw yesterday that on GitHub, notebooks are rendered. So that by itself, you can use that directly. It's not perfect, and it doesn't aim to be perfect. It's probably 90%. In some cases, it'll be 100%. But if you have any kind of fairly interactive widgets or components within your notebook, typically it won't work in GitHub. And it will work in NB Viewer. And I'll show you an example today in the second notebook where there's an interactive map. So it's pretty nifty to know about. And again, it's part of the Jupyter ecosystem. Okay, so that's an alternative that we can follow along the notebook directly without running it, or you can run it. But I'll go directly to the notebook. I've already clicked on the intro notebook. And because I have this small laptop, I will hide the header. Okay, so you know about pandas, or most of you do. Or actually, before I launch into a notebook, any questions or any comments? Yes, Michael.
That a shape file is rarely just one file. It's a collection of files with various projection
Yeah.
files,
Yeah.
XML files, and it's important to keep those together.
Yet another reason to hate shapefiles. And B, another reason why I didn't want to go into it that much. but they're unavoidable. Shapefiles are part of your life for the foreseeable future. Yes?
For the vector tutorial, do we have to create the environment?
Is Amanda here? My understanding is that it's there. If you just click on Jupyter Hub on the notebook, it should be in there directly. You don't have to do anything. And that was my experience 2 days ago. So hopefully, I guess I'll find out soon enough. So GeoPandas builds on pandas and adds a geospatial component. And that means a bunch of different, and cool things. Sorry. Sorry, this is not my laptop. It basically aggregated a lot of great Python open source packages that do different things and put it under one umbrella. And then brought in the ease of interactions of data frames and the pandas ecosystem or the pandas tools. So you have wrapped within GeoPandas powerful libraries for reading and writing vector data. Ultimately, they depend on OGR, which I think was kind of covered yesterday, or touched on yesterday, maybe. And on top of that, there is this Python library called Fiona that simplifies access to vector data, but uses OGR. It also uses this data structure library for GIS or for vector data called Shapely. I've linked into it. And then it also brings in libraries that do GIS operation, like overlays, etc. And also libraries that do reprojection. So it puts them all into a more coherent package, where before it was highly dispersed. So it's very cool. Just like Shapely and just like the listing that I gave you of the data types, GeoPandas operates on those three simple vector data types: points, lines, and polygons. And there are multi-types: multi-point, multi-line, and multi-polygon. And I should say that in case you haven't been as exposed to vector data types or GIS, that just to give you an example of the difference between, for example, a polygon and a multi-polygon, you can take the example of a data set of states, US states, 50 states. There is not a single way to have a shapefile, for example, or a GIS data set that for states. One approach could be that every single polygon, meaning every island, every part that is divided in two, would be a polygon. So instead of having 50 features, you would have as many features as there are polygons. Now, in this part of the states, in Washington State, that would be many polygons. I have no idea how big it would be, but depending on how small the islands are that you include, it would be many, many, many more than 50. There can be valid reasons to have that, but it can also be pretty inconvenient. So another way of representing the data that kind of makes sense is to have 50 features, except that one feature would be one state. And sort of conceptually, that makes sense. And therefore, Washington would be, instead of it being like hundreds of polygons, it would be a single polygon or multi-polygon made up of all these elements, like San Juan Islands, if you haven't gone there, well, tons of islands. Even islands within a lake would be a separate polygon that becomes part of the single multi-polygon. So as you're dealing with vector data, you'll encounter this, that they may arrive as multi-polygon, they may arrive as polygon. It just depends on how the data creator chose to represent them. Sorry. Okay, one thing I'll do is I'll restart the kernel so that I erase previous results, and I'll be generating the results as we go. One last thing I'll mention, or general thing, is that GeoPandas can include information about the projection, basically, the coordinate reference system. So you can assign to it, and we'll have an example of that. But if you want to do an overlay, for example, between two GeoPandas geodata frames, and they are in different projections, it won't handle those differences right away. I can't remember if it'll actually not work. It'll probably work and just do the wrong thing because you're operating on different coordinates. So you have to know in advance that you're working with different projections. But you can query the data frame, the geodata frame, to see if they have the same CRS. And then it gives the tools to convert. GeoPandas is awesome for exploratory data analysis, especially in Jupyter notebooks, but really even outside of them, because it's so terse. And again, especially if you know Pandas data frames, they're really natural, I think. The code becomes highly compact, and that makes and readable, and that certainly improves reproducibility. It's easy to reproduce something you understand more quickly. And if you're reading up Pandas, then or tables like from relational databases, it's a very natural mapping. It's not world peace, though. It's close, but it's not. It probably is not what you would use directly to generate maps that you'll publish in Nature. But you can use it to do your pre-processing on your data management, and maybe you spit out something that then you used in some other package, or both Python or something like ArcGIS, QGIS, or whatever. So it can still have a role in your processing chain, even if it doesn't generate that final, extremely polished map. And performance, I mean, like any other package, it's being improved constantly. There are two areas where performance is being improved right now. You'll hear about Dask on Thursday for parallelization. That's going on. There's another rewriting of the code, another sub-project that is going to make it faster. But it's possible that for really large data sets that it's not super fast. I haven't tested it that way, but watch out for it and let me know. OK, so we'll get going. And I'll just be hitting along to run this. We'll set up all the, or import all the libraries. There's that data folder that we'll be using for some examples. And I'll point this out that I like doing this, again, along the lines of reproducibility. What this line is doing is showing you the versions of some of the libraries. That can be important, if certainly for reproducibility. If you create a notebook that you'll come back to a year from now, which version you used may be important, especially if there are software that are changing. So the first element that I'll cover and I'll start building up from simple examples to more and more complex examples. The first, first thing we'll talk about is geoseries. Again, going back to pandas, if you remember series versus data frames, geoseries are completely analogous. They are sort of the one column or two column table, except that the column here is now geometry. So this geometry objects, shapely objects. So you start remembering them. And an index. That's all it is. So it's made up of an index and a GeoPandas geometry. And just like we discussed a minute ago, it reuses or it represents the same three basic single entity spatial types and their multi-versions, multi-point, etc. One thing to watch out for is that unlike a shapefile and most GIS data sets, formats, in a shapefile you can only have data one type. You cannot mix points and lines in the same file. And that can be annoying in certain cases, but mostly it's a good thing. It can be, given limitations in software, typically data sets are expected to be one type. In GeoPandas, you can actually have a mix. So hopefully, I won't have that situation in these two notebooks, but there could be instances where you end up inserting data of different types in the same data frame. And if you were coming with the, like most people, with the GIS background that a shapefile has only one type, you could be in for a surprise. So just be aware of that. OK, that's all I have for theory. Now we'll start building up more and more complex examples. First, just the simplest possible creation of a geoseries. I'll import the well-known text, or WKT module from Shapely to create a geoseries using the well-known text representation that you'll see in those strings. 0.12, the x and y is 1, 2, totally artificial, just 3 silly points. Wait, I thought I had, give me a second, I thought I had a, when I restarted the kernel, clear output. I forgot to clear output. You don't have to do that. I need to do it both to, for my own sake, so I know where I am, and also kind of makes the creation of the running of the cell more obvious. OK. So we see we created a geoseries with 3 elements, 3 points. That was simple. You will rarely do exactly anything that looks like that, because you would almost never be typing in your code the exact x and y and using that syntax. But it's still helpful to know. OK, so now we'll do something that's just slightly more realistic. Instead of typing the well-known text string representation, we'll use this function from Shapely called point. That does kind of the same thing, except that it's more natural from a programming perspective. You basically pass it values, as opposed to constructing strings. This is actually something you do use, and we'll have an example. But the result is essentially the same, 3 points. And you can see that this is a list of point objects. OK, so what does the type look like, and what is the length of the geoseries? It's a GeoPandas geoseries, and the length is 3, as you saw. We created it from scratch, and there was no information there about projections, so we'll make the geoseries smarter by adding the projection information. And here's the first aid for that test I will have tomorrow, the EPSG 4326. This is lat long, basically. So there are multiple ways of encoding projection information. This is one of them. And what this did is just assigned an attribute to the geoseries saying the projection is this. And then we can use GeoPandas as tools to take that information and reproject and so on. Now, one of the cool things about GeoPandas, just like Pandas, where Pandas, one of the great things that it does is it repurposes the matplotlib plot function to make it a lot easier to generate plots directly from a Pandas object, which is great for exploratory work. Same goes here, that once you have a data set in a geoseries or a geodata frame, it has repurposed the matplotlib plot to generate a simple view, or not so simple view, very easily. So we'll create a simple plot, and we specified, we had a geoseries as GS. We specified that we want to asterisk as the marker, color red, marker size of the figure, and so on. And I wanted to get extra fancy and specify the X limits and Y limits. But that was super easy to generate a plot. Obviously, this is fake data, so not terribly interesting. Okay, so we'll build up a slightly more realistic and complex example for doing the same thing. Now we'll create this dictionary with some attributes and lat and long again. Create a geometry with this scheme that is nice and compact. You take the X and Y, or longitude and latitude, to create these point objects, and then we pass them to the geoseries. And there you go. We've done the same thing in a different way, and this time we control the index. Now we have A, B, and C as the index values, where we fed those values. Okay, so now we're ready to jump into geodata frames. So I alluded to before, a geodata frame, you can think of it as a feature collection. It is a feature collection because you can have as many rows, if you will, or features as you want. And it'll have a geometry column. It can have more, actually. We won't touch on that, more than one geometry column. Okay, so we'll build up on the example that we had. We just created this data. We had this data structure, or a dictionary, that had attributes for A, B, and C, or one attribute, and lat and long. So we'll create a Pandas data frame out of that. And there's the Pandas data frame. This would be a very common scheme, that you have a dictionary, a Python dictionary of information where each attribute is essentially a column. So this is, as opposed to the very first things I showed you, this is a scheme that you will use a lot and you will encounter a lot. And now we do have the geospatial information in there, the lat and long, but they're not, they're just values. They could be length or anything. So we'll take that data frame and create a geodata frame out of it. By using the scheme I just showed you, we create a geometry list using the point function that we saw earlier. And then we pass the data frame and the geometry into a geodata frame. And now we have a full-blown spatial geodata frame. It doesn't look any different. It's still 3 boring points. But now we're using a geodata frame that is much more capable. You can add as many attributes as you want, and so on. Okay, now we finally start moving towards using real data. And this is sort of weird real data, but it is real. It's something that I used with Don. I guess Don isn't here yet. We developed about 2 years ago to operation for this data set is used at 1 a.m. Every 24 hours. It's part of an automated process for this. What is that? Okay. Sorry. Not my laptop. Okay, so we created that shapefile. You'll see it in a bit. So you can see the GeoPandas read files command, and that wraps these other libraries that I mentioned. Basically, you can pass just about any format, common format, to that GeoPandas function to read geospatial files. In this case, we're reading a shapefile. But we use this shapefile that roughly represents major ocean basins. And we use it automatically in this application with ocean acidification monitoring sites globally. So you can see that it has a couple of attributes. So we created a geodata frame and the polygon geometries. And the CRS was read from the, as Michael was saying, the different components of a shapefile, the different files. One of those that is not required, but it's always good if it's there, is the PRJ file, the projection file. So GeoPandas will read the PRJ file if it's present. And you can see here that you can get at the CRS, at the projection, as just a property of your geodata frame. So really convenient. Okay, so what does it look like? Again, we use the convenience of that plot command. That's very simple. And you see these blobs that probably hard to make sense of. But don't worry, we'll get there. What's on the left is North America, or the Americas, I guess. These are a different definition of oceans. They're not coastline oceans, but the midlines run in the middle of continents. But anyway, so this is kind of real data. And the geodata frame is made up of both polygons and multi-polygons because of the nature of the data. And we can get at the geometry types very easily in Pandas by looking at the geom type property. And GeoPandas is chock full of these really useful properties and methods to get at different things like areas of polygons, etc., and get at them very easily. So it's got this geometry submodule, if you will, that you apply on the geodata frame, and then it gives you a number of other useful properties like area. Now, these areas happen to be in square degrees, which are kind of useless. But still, you get the point that you can get at the areas very, very easily for polygons. You can also generate some things very easily. In this case, the bounds. For each of the multi-polygons, a bounding box, basically, as coordinates. Or, potentially more useful, the envelope. So instead of the actual values of that bounding box, a polygon that represents the bounding boxes, and that's the envelope. So on the fly, you can take this geodata frame of polygons, generate the envelope bounding boxes, and plot those bounding boxes very easily. That's the key, very easily. It might seem weird that some of these bounding boxes are, given that it's an ocean data set, actually span from -180 to 180 degrees, so the full globe longitudinally. But that's just the nature of the data, so we'll explore it a little bit. We can use our Pandas filtering syntax, where we take the oceans geodata frame, which at some level is just like a data frame, take the oceans attribute and select for the rows that have oceans be equal to North Pacific Ocean, and plot those. So only plot the ones that have an oceans attribute of North Pacific Ocean. And that's what it looks like. So it's the two sides of the North Pacific Ocean on the east and west. That's why when you create a single bounding box, it'll span the full range of longitudes. And just want to emphasize here how easy it is to do this attribute query and then do a quick plot to see what it looks like. Okay, now we're getting even more real. We'll load a data set that is pretty well known and widely used as a background, natural Earth. And a subset of natural Earth comes bundled with GeoPandas for convenience. So we'll load one of those, the natural Earth low resolution, and that gives you countries. You can see the population estimate, continent, name of the country, code, and the geometry. And we used read file again. I forget what format this comes in, probably shapefile. It came in with its CRS, and again, the PSG 4326. Hopefully you've memorized it by now. Maybe there should be a door prize. So this is the simplest possible plot, almost the simplest. I guess I don't have to have figure size. Well, I should, given that I'm running this right now, and I'm curious. We don't have to have a figure size. So see? It doesn't get simpler than that. You take the geodata frame, dot plot. So again, you can get to useful views very easily. So what we have here in this data set is countries globally. And we'll start doing more fun things. We'll mix this new data set of countries with oceans, putting one in the background. We're putting the oceans, this weird oceans data set in the background, and then plotting countries, the world geodata from on top. And you can see the scheme here that within we have the world.plot parentheses, and within that there is another plot on a geodata frame, so that what's within the parentheses gets rendered first, or in the background, and what's outside gets rendered on top. Now, I fine-tuned it a little bit. I chose what polygon colors or face color to use, what color map to use, set to figure size, etc. If you eliminate all that fine-tuning that I added deliberately, it's still pretty simple. You did an overlay map, and very quickly and pretty easily in terms of the syntax. Okay, but you can also use your matplotlib chops to fine-tune it. And then you get something that starts looking like what you would get from when you do normal GIS maps. So you can see that we fine-tuned the title, the looks, the color maps, etc. And I'm going to stop here for a few minutes to give you time to soak it in, ask questions, talk to your neighbors, to I don't know, play with anything that you've seen here so far. There's a question there? Oh, just stretching, not a question. Hi.
Hi, I have a question about the area. So you said that the area calculation is in degrees.
The area calculation will be in whatever the units are of your geodata frame.
But for that long, it's in
Yeah,
degrees.
yeah. It's not doing anything smart. It's just taking the coordinates as they are.
So if you want to then convert that to square kilometers or square meters or something like that, do you have to use a spherical polar transformation? Is that what you need to do?
There are probably a couple of approaches. If you're dealing with a global data set, if you're not dealing with a global data set, what I would recommend is converting it to some sort of projection that you choose.
Okay.
Because once you convert, you create a new geodata frame in the projection of your choice.
So like a local projection? So in
Yeah,
UK,
yeah. Well, I mean,
international grid,
yeah,
something
local could be continental. There's some projections that are good for even continental scales. And then the advantage of doing that is then you can take advantage, leverage all of that GeoPandas has to offer. Then you know that when you get the area, it'll be the area that you expected.
So when you take a projection, you're looking at something on a flat plane?
Yes.
Right,
Yeah.
Okay.
If you're dealing in a global, so that would be what I recommend in most cases. If you're dealing, especially in a global scale, picking an appropriate projection at a global scale can be tricky for areas. I mean, the choices that you make are trickier. So it may be, depending on what you want to do, that you use some sort of function. Maybe GeoPandas even has one to get at areas in square kilometers from degrees. I don't know the straight answer, but it'll be interesting to find out.
Yeah. Thank you.
Mm-hmm. Any other questions? Can be on anything. Could be GIS, more reasons to hate shapefiles, or why you love shapefiles. Yeah.
So if you want like plot multiple scenes overlay on each other, do you like has multiple parentheses?
Well, so he asked. I think this is worth repeating. He asked if we wanted to do multiple overlays, so overlay plots, like I just did. Would you do multiple parentheses? I think the answer is generally you can do that. But it's not that you have. I showed two styles. One was the simple one-liner with one parenthesis, and then the matplotlib style that is more traditional style where you do one plot, then you tweak it, you do another one. I think there's the point of diminishing returns, where if you have 3 or 4 things you're overlaying, putting it all within this hierarchy of parentheses would be hard to read, unless you're really good about how you organize it. So I would say after 3 or so, it's probably better and more readable to switch to the traditional style. The point I wanted to emphasize is that if you're only dealing with 2 or maybe even 3, this approach of putting it in parentheses makes it so darn easy to create plots that are I don't want to say powerful, but they're very informative and useful. Yeah. Well, thank you. Let me give you the dollar that I promised you. There you go. Sir, thank you for asking the question. That's at the end of the, no way. That's at the end. That's the very last exercise in the next notebook. Any other questions? Yeah, absolutely.
It's not actually related to what you've been showing here, but how, I'm not familiar with
sorry.
Jupyter at all. How do you switch between Markdown and adding?
Yeah.
Like if I add that in there, how do I?
So tell me which one you'd want to do, just to illustrate it.
I'd like to turn this into a
Markdown?
title. Yeah.
Okay. There. That. There you go.
And then when it.
Well,
still looks,
you have to basically execute it. Basically, with Markdown in Jupyter, you have to do the same thing you would do as with Python code. And now I'm so used to using keys, so I use shift return, but you could do run also.
okay.
There you go. So, but the main thing to remember is that you kind of execute in the Markdown. If you don't execute it, it just looks raw.
Right. Okay. Thank you.
Okay. So should we move on?
I have a question.
Yeah.
The use of this bounding box
Yeah.
figure you created, like,
Yeah.
I don't understand why do we need that figure?
I'm sorry.
The
Can you
bounding
point me
box.
to?
Yes, for example, this.
Yeah.
We are not using it anywhere, right?
No, I'm just illustrating one of the features of GeoPandas.
How is bounding box created? For example, you see the shape of this like this.
Yeah.
So basically, it covers like everything.
Yeah, so let me take the simplest example. This one or this one are simple in that the feature here is just this thing. So the bounding box with the rectangle that fits that, that can fit, everything.
Okay.
Again, in this case, we're not going to use it afterwards, but it's a pretty common operation.
Okay.
For example, if you're creating metadata, you'll define the bounding box so
Right,
that
you
a
need-
search mechanism will find it.
Right.
And sometimes if you're doing certain quick operations to define what matches that area, it's a lot faster to operate in bounding box than Polygon. So just a common operation and just an illustration of how easy it is to get at these common things. Okay, so we'll be moving on. Okay, so we'll keep expanding in capabilities and the illustrations. Now we'll illustrate reading from a PostGIS database. It'll be a simple data set. And this PostGIS database happens to be hosted on the cloud, on an Amazon cloud. But that becomes kind of irrelevant. The way it doesn't, the style and the syntax that we're using will be the same if you were operating on the database on your server environment in your university or in your computer. I don't know, just out of curiosity, how many of you have experience with relational databases? Oh, it's about a little less than half. Okay, nice. So we'll be using to interact with PostgreSQL. We'll be using the PsychoPG2 library. And then because you always want to be careful with credentials with databases, we'll be opening this file that has the credentials. Yes?
What is PostGIS just like a type of data format extract file, or?
So PostgreSQL is a relational database. PostGIS is the name for the geospatial extension. But it's so widely loved for good reasons that people refer to it as just PostGIS. The fact that it's in PostgreSQL, it's an extra that you don't need to mention. But it is the name for the geospatial extension.
It's like open source.
It is. PostgreSQL is extremely capable open source relational database system. So PostGIS is also open source. Very powerful. Saying we'll scratch the surface doesn't do it justice. We'll just interact with it, but won't touch it much. So first I read this text file that is, we're reading from Jupyter Hub. Oh no. Oh, so I skipped one. Okay, good. So we read the credentials, and then this is the common mechanism for passing a credentials file to PsychoPG2. And just to give you a taste, if you haven't done this before, for what that file looks like. And also for adopting good practices. One of the great thing about Jupyter Notebooks is that they're so easily shared. And that can be dangerous if you're passing around sensitive information, whether it be the results of an analysis, like privacy issues in analysis, or whether it's passwords that you embedded in your Jupyter Notebook because it was so convenient. So here's just one scheme for if you're ever reading a credentials file and you still want to show some things but hide others. Here before we did a print, basically we hid or erased the user and password. But that's what the credentials file looks like. The host is that Amazon cloud address. Okay, so we will now read using the function that comes with GeoPandas, read PostGIS, the world sees dataset, and using, for those of you who have experience with relational database, you'll recognize that query syntax, the simplest possible query. Bring me all the columns, no filtering, etc. We're passing the connection information that we just loaded, and then this extra parameter or argument. Okay, so now it's reading from the cloud, and you'll see the data set in a bit. It's a lot more interesting than the oceans data set I just showed you. And there it is. And it read also from PostGIS. It read the CRS and assigned it to that property, so yay. Okay, and I'm just going to close the connection now because we read it into memory. And we can be good citizens with our connections to systems and close it up. Okay, so now we do the head command to see what it looks like roughly. And again, we have some IDs, a name, some attributes, oceans, and geometry. Now we'll take this to do fancier plotting, but still leveraging the simplicity of GeoPandas, the convenience for exploratory analysis. So we'll take this new geodata frame called Seas and do a plot. This time we'll do a categorical plot by passing the column oceans. In other words, it'll render each unique attribute or value of in the column oceans with a different color. And it'll show a legend automatically. And so that's a pretty nice plot and reasonable plot for such a simple one-liner, if you ask me. So this, just FYI, it's hard to see. There are boundaries. I think you can see it in the orange. There's some thin white lines. These are what's often called seas. So if you take ocean basins, that's the larger North Pacific, South Atlantic, et cetera, this would be subdivisions like Gulf of Mexico, Caribbean, Mediterranean, et cetera. And while I'm here, I should mention that I've tried to add quite a few links and extra text within this notebook and the next one, not so that you read them right now and fully absorb them, but just so that you have more resources to go back to this week and afterwards. So keep that in mind, that in addition to the code, there are a few other resources sprinkled in. Yeah?
So when you plot this, it knows the plot, kind of the polygons that it's plotting?
It knows it's a polygon.
Right, so it just picks the polygon, because last time it was called geometry, that column, and the other time, this time it's called geom or something like that.
I'm sorry, what are you looking at? Just to.
So when you're plotting.
Yeah, because I don't think I referred to anything.
So I'm just going off the column name. One time it was geometry.
Oh, okay, so you're still up there.
I don't know which column plot if you say. Maybe had multiple ones or something.
Interesting. Sorry, let me answer this, and maybe you were were you trying to answer it, or?
Yeah.
Okay, go ahead.
I think for those attributes, you can change the name of the geometry column. You just have to know which one it is.
That's ultimately the reason, and I'll have an example of this, of dealing with this potential confusion in the next notebook. But there are two things to keep in mind. One is that the name of the column can be anything. It can be My Beautiful Polygons, that's the first thing. So the second thing is what he was referring to. There's an attribute in the geodata frame, just like the CRS attribute, that defines which column, what's the name of the column that is the geometry column. The default is geometry. And because of this default, often you'll run into packages that use GeoPandas but are assuming geometry. And if they don't see geometry in there, a column named geometry, because they made this hardwire assumption, they'll fail. So I'll show an example in the next notebook that changes the name of the geometry column just to make those packages happy. But that's a good question. And then I should say that in the plot, since you started asking about the plotting works off that geometry definition. So I don't have to specify the geometry because it'll just say, oh, geodata frame, tell me what your geometry column is. Yeah, great question. Okay, so now we'll start flexing all these cool leverage capabilities that we have within geodata frames. We have all the coolness of data frames for handling attributes and filtering, and now we've added this geospatial capabilities that are almost as simple, as straightforward to use as data frames. So we can do a filter that takes advantage that is based on attributes, the same one that we did, seas, oceans equals North Atlantic oceans. Well, sort of the same one that we did, except it's a different data set now. And also a geometry calculation, the area less than 1,000. Keep in mind that this is square degrees, so it's sort of hard to wrap your head around, but it doesn't matter. This is a number I picked ahead of time to generate a map that's interesting. And now we rendered the result of that map, of that filter, both spatial and attribute filter, using what we've learned, the scheme of one plot within another, and then we tweak the boundaries just so that we zoom in, basically. And that's the result of that nifty but simple filtering that we applied. Yeah?
Do you mind going over the filtering a bit more of the
Yeah.
seas and the oceans?
Yeah, yeah.
It seems like the column should be seas, and then, yeah, I'm a little confused.
So let's go back to the geodata frame. So this is the geodata from seas, and these are its columns, and oceans is one of the columns.
Because that's the name of it.
Yeah, maybe you were confused with the previous. Good point. I hadn't thought about that. Yeah. Yeah.
So you selected or used the filtering of Panda, I guess it's Pandas right now. Would you also do just in straight SQL for efficiency purposes, for instance, if you have a very big data set instead of loading the whole thing? Would you also just do a SQL query to do that filtering?
The answer is yes, and actually I don't have another dollar, but that's we'll touch on that in the next notebook. Okay. But let me illustrate where that would go. Here, I assume you know SQL. You see that there's a star, and that there's no where statement. So that's exactly what you would do. If you knew you were going to only care about the North Atlantic Ocean, then you should do that in advance, because then you'll be operating on lighter data sets. This would be the scenario where you want everything because you are going to be doing different things. Okay. And now here I'm going to filter on just that. Okay. And now just to show you how simple it is to write data, write to files, we illustrate the use of the toFile function to write to a shapefile. Now, this shapefile will be written to your data subfolder in Jupyter Hub. You can use it if you want. It's kind of boring, but you can use it. Okay, the next example of additional things. We just read from a geospatial relational database that happened to be in the cloud, so it happened to be a remote query. So, and now we'll do a different kind of remote query. We'll use an OGC or Open Geospatial Consortium web service, standardized web service request for this web service type called Web Feature Service that returns features, and transform the response to get it into a geodata frame in as few steps as possible. This web service that we'll be using just happens to be one I manage. It goes back to this global ocean acidification observation network, and it'll be a point data set that where each point is a monitoring station or location where data is being collected. Okay, so we'll run this. We're loading 2 new libraries. Request is for web services or web access, GeoJSON. It's a very convenient library for passing around and converting GeoJSON-like objects or strings and converting to other convenient things. So here I just specify the URL, and don't worry that you don't have to come out being an expert in WFS. You're probably not going to see it often, but it is an important web service for a vector data set, web service type. The main point here is that we define the URL here for the web service endpoint, and then we define the parameters. In this case, this is basically the layer name, and we want JSON, which essentially means GeoJSON, and then we issue the request. There's the URL and the parameters, And here's part of the magic, where we use the GeoJSON library to take the output of that request, which is basically a string, a JSON string, and created an object that is GeoJSON-like. So now back into the territory that we can interoperate with GeoPandas. So let's see, have I run that? So I have run that. So I should have all this data loaded already. And we'll examine what that looks like. It's a GeoJSON feature collection. Here's the language again, feature collection. It has 572 features, and other attributes. We use the GeoInterface method that I described earlier to look at that content. But that's just for exploration. Now we'll pass that on directly into a geodata frame. You can see here that we used the from features method from a geodata frame to read it directly. So this thing that almost directly from the web service, right here, can be sucked in to create a geodata frame very easily. Ta-da. We have a geodata frame. Now we can visualize it. So we're using the same scheme as before. The world plot is inside as a background, and the dots are what we just brought in. So step back of what we did. We issued a web service, a request to an external server to bring it in. We requested JSON or GeoJSON, and then we used 2 steps to create a geodata frame out of that output. And once it's in a geodata frame, we can do what we know how to do in geodata frames. And just as an example of what came through in that web service request, it's points with a lot of attributes. Some are empty, but Indian Ocean, there's a geometry, some URLs, locations, yeah, just a bunch of attributes. Okay, so we're moving on to the next notebook. You can why don't you take a few more minutes now to, again, ask questions, or talk amongst yourselves, or help each other while I switch to the other notebook, and then we'll keep getting grander and talk about more fun things.
So what happens when you make a request, and would it sometimes not know how many features are in that? Is there an error that's thrown, or is it more complex to give you an answer?
There are general answers and specific answers to this. I don't want to make this too much about WFS specifically. WFS happens to not have a good handling of if it's going to return way too many or more than it can handle. It doesn't have a good mechanism for saying, no, I can only give you 10,000 at a time. Or, no, I choke. In general, so there's no good answer. And you don't know in advance. You as the user wouldn't know in advance how the server implementer chose to handle that. More broadly speaking, and maybe more useful in web services, when you're interacting with remote data sets via web services, if you're the creator of that web service, you'd want to have a mechanism, for example, to give the user an expected error or message saying, too big. Do this to give a request that will get data. Or, again, paging. I can only do 10,000 at a time. Here's the first page. Any questions or thoughts? Yeah.
I don't see the from features thing documented in the GeoPandas documentation.
Off the top of my head, I can't point you to it, but given that it's a method on a geodata frame object, actually, maybe this is a good time to illustrate one cool thing about Jupyter. It's a cool thing about Python, but also about Jupyter. I will answer your question directly. And, Okay, so there is the method call that you were talking about, the function, geoDataFrame and dot from features. If you're like me, I never remember what argument it expects. So if you do question mark after the function and hit, you run the cell basically, and I do shift enter, you get the documentation for the function. That's always really convenient, and one of the nice things about Jupyter, that it's at your fingertips basically. But something like this should be online somewhere. I mean, basically that string is in the code. Okay, we'll move on then. And here it'll be, well, building up, but with new data sets, but progressively more complex examples. We'll load our packages again. We'll read a data set from PostGIS, and we'll read the credentials file. And the core data set that I'll be using, it's called hydrobasins. It's a global data set of watershed units with a lot of attributes that define hierarchies for if you have these watersheds that may be, I don't know, a few hundred square kilometers, they have built in some codes that define how they aggregate, for example, into the Mississippi or larger basin. The data set we'll be reading from this Amazon Cloud instance is not the whole globe, it's North America. Some of you may find this useful in your projects, so it is accessible. And there are links here for where to go. I've also added a link to this nice tutorial from the eScience Institute about SQL and geospatial data processing. If you want to know more, I forget your name, but since you were asking about that, that has a lot of details, way, way, way more than I'm getting into. So we'll do the same thing we already did. We read from the database, and here's what you were asking directly. We have a where statement. And this is a perfect example because this data set, again, all of North America with watersheds that maybe just a couple of hundred square kilometers. I forget, I actually don't know how many polygons this data set has, but it's many, and we are operating remotely, so we don't want to be loading tons of data that we're not going to use. And this is the case where, if you know SQL, we pass this where statement, the filter, to the server, and the server does the hard work and just gives us the subset of data that we want. And I know in advance that the FAFSTETR level 4 code of 7831 will give us Western Washington, basically. And you'll see it in a bit in a map. And this is a case also where the geometry column is not geometry. It's called polygon geom, so I have to specify it by hand. I wish GeoPandas was smarter and could read it from PostGIS. OK, so now I'm issuing, and that was the query, and that was fast. Because, again, the server did all the hard work. And it read the CRS. It has 413 features, polygon features. And we'll take a look at what those features look like. Most of those, especially if you don't work with rivers, so watersheds would be fairly unintelligible. FAFSTETR, just FYI, is a fairly well-known, not universally known, but fairly well-known mechanism for coding watersheds in a hierarchical way. But you don't have to worry about that. Now we'll generate a simple plot that using what we learned already. Specify, I know I want to operate with the FAFSTETR level 7. Again, this is a categorical plot. I played around with different color maps that would give me different, that would make sure that every polygon was a different color, and found tab 20. The lesson of this, though, is get to know your data, what it is you're trying to plot, whether you're plotting categorical maps, more continuous maps, or so on, and then you can go to the Matplotlib page to get a list of color maps that you may find useful. And there's a link in there. We are here somewhere. And each solid color is a FAFSTETR level 7 unique code. You see that there are thin white lines, though, within each solid color, and those are the individual polygons that came in the data set. So the basic unit of watersheds within this data set. And you can see that there are a bunch. There are about, 18 or so solid colors, and originally 413 watersheds. And this is in lat long, 4326. So here's going back to your question. Sorry, I don't know your name, but your question about the geometry name, and exactly what I was saying, that there are packages that hardwire an expectation of a geometry column called geometry. And we'll be dealing with two, folium and raster stats, that kind of have that expectation. So I went ahead and renamed the column. So polygon geom, the original name, to geometry, and then did the other step that I was talking about, where you assign the property geometry column name to geometry. Now we can forget about it. Okay, so dissolve is a pretty common and really useful operations in vector GIS. We'll basically take all the neighboring polygons that have the same value. The boundary separating them will drop out, and you'll create the largest individual polygon that had a shared value for that attribute. So here we choose which columns we're going to preserve. And we applied the dissolve method that, again, very handily is built into GeoPandas, but it actually leverages other libraries, other Python libraries. And we specified that it'll be dissolved by the fapsteder7 attribute. You can specify what type of aggregation it'll be, and so on. So we run that. And the result is 7. So we created a new geodata frame called Hyderabad WWP7. It's got 17 features. We can take a look at that. fapsteder6, the lower the number, again, you don't have to know this, don't worry, but a fapsteder6 will have, it's coarser than a fapsteder7. I just carry it over for convenience. Okay, so now we can do a convenient plot, just like before. This plot is just like the other one, except that I tweaked it a little bit, but the main thing is that you don't see those internal boundaries now because they've dropped out. We dissolved them away. So now we're dealing with 18 features or 17. So that's bread and butter in vector GIS and pretty darn easy. Okay. We'll illustrate reprojections. Python has some libraries that let you explore projections. PyEPSG is one of them. So in the first place, we looked at how to assign a projection to the CRS of a geodata frame. In this case, I'll read it back and sort of parse it out and pass it to this PyEPSG library, just so that I can know a bit more about what EPSG 4326 is. And by the way, EPSG has become the de facto coding system for projections and datums and such. It's kind of quirky that it did, because it stands for the European Petroleum, I don't know what the S stands for, and G, I don't know what the G stands for. But it came from the petroleum industry. For some reason, they did a good job. People liked it in the wide communities, and now it's the de facto most useful standard for passing around these codes. I am going to convert this to EPSG 2927 because you wouldn't know what that is. So I used the PyEPSG library to give us some information about what it is. The Washington South in feet. Basically, that's a linear or projected projection that is widely used in state agencies and local agencies here in Washington. And you can see here that we can use the 2CRS method to convert from its original CRS to this new one in a very easy way. So I'm creating a geodata frame out of the previous one by just reprojecting. Okay, now we plot it the same way we plotted everything else. And it kind of looks the same, obviously, but it's now sort of deformed, or rather formed correctly as opposed to geographic. And you can see the coordinates on the axis that are now in feet. Okay, so now we have data that is in more natural units, or that you can operate on more naturally. It doesn't have an embedded area. Well, you can get the area in square feet very readily, but square feet are kind of hard to picture or think about, I think. So I'm going to calculate, create a new attribute using standard pandas data frame syntax, and taking the geometry of that area that we saw before and convert from square feet to square miles. My apologies to those of you who are not from the US, but just cultural lesson, I guess. So now we added a new attribute that's pretty useful. It's area in square miles. Okay, well, you may have a different definition of useful. And now we're going to do a plot, a choropleth plot, or in other words, dividing the ranges, in this case area, and creating kind of a classified plot. It is working. This warning, I won't go into too much, but it talks about this PySal library that is awesome. I never really used it, but I wish I had the application. You may want to use it for your project. It is just mind-blowing in terms of the capabilities it has for analytics and plotting. It's undergoing a major version change and a major transformation. That's why they're giving you this warning that what I'm doing right now works with this version, but beware, it'll go away. But the syntax will change. So you can see here that the standard matplotlib syntax, setting the title, and then the plot arguments are sort of the same thing we've been doing, except that now we pass the scheme. Fisher-Jenks, a common way of slicing ranges of values. And what color map we wanted. And the reason PySal is used is because it's used behind the scenes, and yet another thing that GeoPandas leverages to apply this Fisher-Jenks segmentation scheme for segmenting values. Okay, so now we see that it also gave us this legend directly. The values are an incremental color map where darker is larger, and this is just watershed area. So not the most helpful map, but still. Okay, I had a stopping point here for letting you work on your own, but why don't we stop just briefly to give you an opportunity to ask questions, and then I'll keep going because I'm running out of time. Questions? Yeah.
Just so you're using a lot of these like matplotlib as a basic definition. Is pretty much everything that you would be able to use in matplotlib usable here in GeoPandas in terms of like?
I would say something like, well, 90%, 80%, if you will. Some things, matplotlib is very broad, so some things might not make sense, and other things maybe haven't been implemented, or haven't been implemented in the full breadth of flexibility that matplotlib gives you.
And is that like documented anywhere? Or do you sort of have to just?
The plot function is documented. And you can do the same thing I was just doing. You can go, for example, here, I had name of geodataframe.plot. You can do the same scheme I showed you before, would put a question mark at the end, and then hit shift return, and you'll get that documentation of the arguments. But there's also a website for GeoPandas that'll give you the same thing, essentially, except more nicely formatted. Questions? So after this, at 10, so in 15 minutes, we have a break, and I'm happy to answer any questions, or anyone else here who is a GeoPandas Pro can answer questions. And if I get to the end before 10, also happy to answer questions, or you can work on your own, whatever you prefer. Any more questions then? Okay. Now we'll switch to another cool example. While still using the same data set, we're going to illustrate Folium. And Tony, okay, you know who Tony is, will be describing Folium in way more detail on Thursday in his visualization tutorial. So this is just a taste of both this cool visualization or mapping library, and also how great it is within Jupyter Notebooks, that you can generate this interactive thing, and then it remains interactive. Okay, so we're going to generate a choropleth map, just like the map we created now, except that it'll be interactive. So there's the same geodata frame. We start a Folium map basically by passing a center point, what zoom level, and what background overlay we want. And then this is the choropleth statement, where we specify where the geometry comes from, where the data comes from, what columns we're passing, and what columns we're using to map. How do you connect between the geometries and the data, and so on. But I'll just run it. Okay, so there is a map. Again, it's kind of like the same map we saw before, except it's actually interactive. And now I could, if you wanted to get fancy with Folium, you could have each polygon be clickable and get attributes. That wasn't my goal here, but you'll get some of that with Tony. So that was pretty easy. Take a geodata frame. The hardest part is just figuring out the syntax here. It's not ideal, I would say, but once you look up the documentation, it can do cool things. And again, this is just a tiny sliver of what Folium can do. And when we save this Jupyter Notebook, that interactivity that we demonstrated, the fact that you can zoom and map and click, kind of click, I guess, remains in the notebook. It's amazing that how notebooks implement this. And when you post this notebook online, I guess it is posted online under the Geohackweek tutorial content. If you render it not in GitHub, you won't see that map on GitHub. It's one of those things that don't get rendered by GitHub. But if you pass that link on MBViewer, you'll get it just like you're seeing it now. So it's kind of semi-dynamic in the sense that you're not running it again, but it's fully interactive. OK, so now we'll illustrate spatial joins of polygons on points. And for that, we'll be using a GIS file that is in the data subfolder. It's in another format, GeoPackage, that is intended from the Open Geospatial Consortium to be as a replacement to shapefiles. It's not going to happen overnight. And it's based on the SQLite format, file-based relational databases. And of course, GeoPandas can read that just as easily as shapefiles. So you can see that it read the GeoPackage, and it's got 194 features. We'll take a look at the first one. NANOOS is the Northwest Association of Networked Ocean Observance System. I'm the data manager for NANOOS. Those are basically stations where some measurement is made based on sensors of marine environment. And this is, you could say this is metadata about that station. OK, now we'll generate a simple plot of those points. It's hard to wrap your head around this, but I'll just, for orientation, what's on the right, the upper right is basically where we are, Washington. And the bottom is the bottom of Oregon or Northern California. OK, so those are points. Now we're going to assign the watersheds, the solid watersheds to each of these points, or at least the points that fall on land, so that we create new spatial information or add spatial information to these points. And for that, we do the GeoPandas S-join or spatial join operator. You can see that we're passing 2 data frames here, and we also pass the argument how, what kind of overlay it is, an inner overlay, or join rather. OK, so that resulted in 63 points, and the outcome is points. We're taking these polygons, sort of putting them on top to assign attributes, and we get 63. We started out with 193, but most of those fall outside of, because they're marine, they actually fall on water, so they're not within the bound, within any watershed polygon. And there's a simple map again, showing the dots, the original dots, and the watersheds. OK, and now getting to your question, overlaying rasters and polygons. And that's the last example that and think of this as a segue into the next tutorial that we'll be talking about rasters. And these things are not isolated. Like Anthony said initially, typically we work with all these data types, and typically you'll be mixing and matching. The nice things about tools like GeoPandas and data structures like GeoJSON is that have become widely used as the lingua franca to communicate is that raster tools will now expect a GeoPandas geodata from a GeoJSON. And if you have that, if you turn your data into those forms, it's very easy to communicate that information to raster or other tools, and vice versa. We'll use this really lightweight and highly focused package called RasterStats, and the PRISM national precipitation data set for July, monthly for July. And just read it. Well, first we define the file path, and this is also in the data subfolder. And we'll use Rasteria, which you'll hear a lot more about later today and throughout the week, to read this TIFF file, or GeoTIFF raster file. We'll open that file using, again, Rasteria. Here's just reading some of the metadata that comes from that GeoTIFF. And again, EPSG 4326. See? There's a reason to memorize it. And then Rasteria comes with also with this simple plot called show. That just shows you what the raster looks like, roughly. But we don't care about the raster. We care about the vector. again, those of you who've been exposed to GIS raster operations will at least recall the category zonal statistics. So basically, that just means that on predefined areas that you apply some statistics. It could be average, it could be a summation, it could be a minimum or maxima or standard deviation. In this case, our areas will be the dissolved polygons that we dealt with earlier, we created earlier, and the field of raster values will be this precipitation. So we'll overlay, if you will, the dissolved watersheds on top of this precipitation to come up with mean precipitation for each of those watersheds. So we have the geodata frame already created. We just loaded the raster. And now we're going to load or import raster stats and apply zonal stats. Here's the geodata frame. Here is the raster. In this case, I guess it's using the, it's going to reread the data. So we're passing the file path. And we tell it that we want the GeoJSON output format for convenience. Ta-da, it's done. 17, there were 17 watershed polygons, and we got 17 back. What we get back looks like that. It's a geodata frame again. Or rather, it was a GeoJSON-like object, and we used from features, just like we did before, to convert it into geodata frame because I don't know what to do with stuff that's not in a geodata frame. You can see that it gives us multiple statistics. There it can count how many cells or pixels there were, maximum, mean, and minimum. Now raster stats gives you some control on what statistics to get, but I just wanted the usual. And now we're going to generate a more interesting choropleth or a map of values, polygon values than area. So now this is the result of what you could call totally bona fide analysis. We started out with pretty small watersheds, and we aggregated them to something that I thought was more interesting, these larger watersheds. So we used dissolved. Well, we first read the watersheds from PostGIS on the cloud. We dissolved using GeoPandas coolness. We read this GeoTIFF and overlaid the two and calculated mean precipitation for each of these watersheds, and that's what we're seeing right now. And this plot here is probably the most tweaked plot that you'll see in my two notebooks. One of the things I added was the positioning of the legend box, for example, in the upper left. Otherwise, the default would be the upper right, which is not good. And that's the end. I added some resources towards the end that you may find useful. For example, you can go into the GeoPandas documentation to read more about the operations that it has available. It's a lot more than what I presented. I mentioned PySal. Again, it's really impressive. I don't know if we have real vector analytical pros in here, but maybe even some of you have already used PySal, but it just looks really impressive. Just be aware of that version change. You'll see, or you'll hear more about some really cool libraries from Tony on Thursday. Now, his tutorial is already online, so you can check it out also. But in particular, Cartopy and GeoViews are pretty fantastic. Plus a lot more on Folium. Now, if you want to be adventurous, there's this library, kind of small, but it looks really cool. I haven't used it, called Geoplot. It's in the Conda environment, so you can play with it. This same environment that you're using, you'd have to go to the documentation, but there's a link in there for a gallery of Geoplot. Basically, it gives you more options. It assumes that you'll be working with GeoPandas, geodata frames, and geoseries, and it allows you to create a wider variety of plots that are also generated pretty easily without having to go to the excruciating detail of Matplotlib directly, or Cartopy with Matplotlib. And there's also some links to other raster resources, including the, well, like I said, you'll be hearing more about raster later today and in the XRA tutorial. And I'm sure they'll be touching on how you use vector data there to do raster stuff. I suspect that region mask will be mentioned on the XRA or NDRA tutorial. But anyways, you can refer back to this at your leisure. And that's that. Thank you. Let's thank Emilio.
Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank Emilio. Let's thank appreciate it. We're going to proceed to coffee. We'll have 30 minutes, so lots of time to chat. Come ask Emilio more questions over coffee if you have more things you want to talk about, and we'll reconvene at 10:30.
Should I stop it?
Yeah.